So in the second part of discussion on soil aeration and soil air, we're going to talk about one of the ways that we measure what we call aeration reduction potential of the soil. And really what that gives us a measurement of is not necessarily the presence of oxygen, but the capability of the soil to either be more oxygenated or be less oxygenated. And so we use this terminology to, and we have a device that can measure this in the soil. This thing called redox potential here, and this word is just formed from these two things here: reduction and oxidation. Okay, and if a soil has plenty of air moving through it, then it is oxidized. If a soil has standing water in it for a long time, it tends to be reduced, or what we call reductive. And there's a lot of chemistry that goes on into this. If you've had chemistry, you probably studied oxidation reduction reactions. Our purpose really isn't to go into the chemistry of that here, other than to know that the chemistry of the soil and the aeration of the soil, or the lack of oxygen in the soil, causes changes in the soil. So it tells us things like the availability of elements to plants. So iron can be in more or less available forms based on whether or not the soil is oxidized or reduced. Same thing for manganese, nitrogen, sulfur, other nutrients can be affected by whether or not the soil is flooded or well aerated. So that's called oxidation or redox potential. We can measure it with this device that you see here, and an idea of availability of nutrients. Here's a table that just shows you some of the elements over here that can be changed if they're found in an oxidized soil. Okay, well oxidized, plenty of oxygen in that soil, or if what happens when we take them and put them in a non-oxidized condition. So maybe we flood them and it takes away the oxygen that's in that soil air. What happens? Well, nitrate, this guy, we'll see this guy later, she turns into nitrogen gas possibly, or ammonium. Okay. Iron goes from one form to another. Carbon goes from CO2 to other forms associated with hydrogen. So you can see there's definite changes if we again either flood the soil or have a soil that has plenty of oxygen. To the topic of soil drainage, and soil drainage is important. In Chapter 6, you saw that artificial soil drainage actually is very important in many places that produce a high amount of food crops. So often we find ourselves in the Corn Belt needing to drain a field in order to lower the water table so that plants can grow. But we can also just take a look at the soil. If we don't know about whether or not water stands in a soil for a good time, we can take a look at the soil, and we can look at the colors of the soil and get an idea, especially the profile, the horizons that are lower down in the soil, and we can get a really good idea of whether or not that soil has some standing water in it at a point in the year, or for a longer period of time in the year. So we have some rules about this, and we'll see some more of these in just a second. We ignore blacks. Okay, we ignore organic matter that's in the soil, and grays that may be associated with organic matter. If it looks organic material like, then we try to ignore that. We're really looking at what's going on with the mineral, the rock-derived mineral soil. And the other part of this, the other difficulty of this, is that typically soils that have poor drainage actually increase in organic matter. So, for instance, think about a wetland soil, if you will, if you've ever seen some of those. So in that wetland situation, we've got high amounts of plant material that can actually grow in those situations, And we get, even if we don't have high amounts of plant material, we still have organic matter that's collecting and not being broken down. So soil microbes won't be as active in breaking down organic matter in situations that are poorly drained and we have water standing on those areas. So sometimes organic matter comes into the mix, but there's other things that we look at to see whether or not soil is poorly drained. There's other ways we can tell if soil is poorly drained or not. This is a poorly drained soil that over time increases in organic matter in that soil. So you can see on the right-hand side we have higher organic matter, darker soil, but I can tell you that these are all in a poorly drained situation as we move forward. In terms of how we tell whether or not we've got a poorly drained condition, one of the first ways we tell is if our soil appears to be in this area of the Munsell color chart, so chromas of 2 or less. So again, we're looking at chromas here, and if we find ourselves in the 2 or less, we may be dealing with a high water table that produces very poor drainage in the soil, and what we would call reduced conditions, and that gives us these grays that you're seeing here, and mottles. So here is one of the key concepts in soils. If you look into a soil profile and you see these splotchy areas, what's happening here is, remember we talked about iron changing forms. So iron, when it's oxidized and has plenty of oxygen, is rust-like. So it's this orange that we're seeing here. Iron, when we place it in a low oxygen condition or a reduced condition, let's say we submerge it in water for a long time, it will start to turn gray. So it'll go from this red into a gray color. And so what we find is if we have a water table maybe moving up in a soil for a period of time, let's say 3-4 months, and then moving back down into the soil, and then moving up for 4 or 5 months, and then moving back down, some of this iron is going to turn into the reduced form of iron, but not all of it. So you still have these areas that are gray, that are orange, that are still oxidized forms of iron. So this is one way we can tell. If you've got models that look like this in the soil, these splotchy areas like this in the soil, you know that you're probably dealing with soil that isn't saturated all year long, but there's a period of time in the year when this soil is saturated, or it has been saturated. So we can tell that by at these models in the soil. This is a what do I want to call it? A series of soils that, as you move towards poorer drainage, you start to see more mottles. So in this soil here, there's not very many mottles. It looks like a well-drained soil. In fact, it has that in the name there, well-drained. Sorry, here. Okay. Here's another imperfect. They'll call it imperfectly drained. We'll give it another name here in a second. That you can start to see in this area right here. You can start to see that splotchiness showing up. Okay. More red, more orangish than it is gray. But as you move over time, again, you see that splotchiness, but now gray dominates. The gray dominates the color scheme of this soil. There's still a few areas where we have models of orange in a gray background. So that again shows us that we're dealing with a drained soil. So we can distinguish how oxidized, how well aerated or reduced, poorly aerated a soil is by these colors, by the presence of models as well as the soil colors. So we have classes. We have 4 classes that we can break down soil into. We have a well-drained soil. That means we have no models above 30 inches. Okay, so above 30 inches, there's no models. Below 30 inches, there can be all the models you could ever think of. And if the soil profile is 60 inches deep, for instance, and we have models at 30 inches and below, no problem. We can still consider that for our purposes, in particularly engineering and crop purposes, that to be a well-drained. The next category is moderately well drained. So we have gray mottles above that 30 inches, but they're not above 18 inches. So 18 to 30 inches, we find mottles in those places, in that area in the soil, those depths in the soil. And we've got a moderately well-drained soil, so grows above the 30 inches but not above 18. The next category is somewhat poorly drained, so we have gray mottles closer to the surface. So above that 18-inch mark, we have gray mottles in a brown background. So you saw in the last slide we had a brown background with some gray mottles in it, or an orange background with gray mottles in it. That's somewhat poorly drained if we find those mottles above 18. Poorly drained is mottles above 18 inches, except now we're dealing with a mostly gray background, telling us that the iron in that soil is in a reduced form, and telling us most likely that we have a very high water table that is in that soil for extended periods of time. Okay, so what we do is we will determine a soil drainage category from looking at a soil profile description, some steps, and then we'll come to that slide here in just a second. So we look at a profile description, just words that describe different layers in the soil, like you've seen before. We look at the colors there. If we see chromas, so remember when we look at color, we might have a 10YR 3, 5. Okay, this number here is the chroma. Okay, hue here, value here, chroma here. So we're looking at that number that's on in the denominator of that fraction. So chromas of 2 or less might indicate that we have drainage. Okay? And we want to look at the depths that those chromas occur. Okay? We determine drainage, especially as it relates to mottles. So really, one of the keys that we see is mottles. So let me go back to this to the drainage categories here. So I'm going to bring in a let me see if I can do this. I'm going to paste in this document here, and what we're going to do is we're going to take a look at this and see if we can determine the drainage class. So here's a typical soil profile description. So we have an AP, let me get the pen out, an AP, horizon 0 to 6 inches. We have a chroma here of 2. Do we have any mottles here? Fine granular structure, friable. No, I don't see any mottles. It would describe it in the words following that color. We move to an E horizon, and we've got another fairly light chroma here, but it doesn't look like it's describing any mottles. Here we're dark brown. The chromas aren't 2 or below. We're reading this. We don't see any mottles here. Again, we're in a B2, so we're here. Any mottles? Don't see any there. And again, pay attention to where we are in terms of the the depth in the soil that we are. B3. Here we go. 19 to 30 inches. No, I still don't see any mottles. Oh, wait, there it is, right there. Okay, see that grayish brown mottles at 19 to 30 inches. Okay. So move this over here. So at 19 to 30 inches, we start to see mottles. Well, where are we on this? Here, well drained, no gray mottles above 30 inches. Well, we do have gray mottles above 30 inches because at 19 to 30 inches, here we have mottles. Okay, well, let's move to the next one. Gray mottles extend above 30 inches, but not above 18 inches. Okay, I think that's probably where we are, right? So we have them above 30 inches, so in the 19 to 30 inch category, we have mottles, but they don't extend, they're not above that 19-inch mark. So we would, in this particular situation, we'd be dealing with a moderately well-drained soil. So we can categorize things based on their soil profile descriptions. That's kind of a handy thing to have, a handy thing to know. That'll end our discussion on soil aeration and drainage. The next section we'll get to is soil temperature.